Now, a lever is a simple machine consisting of a rigid bar or bone that rotates around a fulcrum or joint and is used to transmit a force. Now, there are four parts to a lever: the lever arm, the fulcrum, the effort, and the load. In the human body, bones act as levers and joints act as fulcrums. Muscles provide the effort and force to move the loads based on the arrangements of the joints and muscles. The human body is made up of three different classes of levers. The first type of lever is a first-class lever. These levers have a fulcrum in the middle, like a seesaw. An example of this is the joint between the skull and the atlas vertebrae of the spine. The spine is the fulcrum, across which the muscles lift the head. The second type of lever is a lever that carries the load in the middle, such as a wheelbarrow. An example of this type of lever is the heel joint. In this case, the upper body provides the resistance, or load, and the heel acts as the fulcrum. The effort would be the contraction of the calf muscles. The third type of lever is the third-class lever. Third-class levers have the effort in the middle, but offset to one side. An example would be the elbow joint. When we lift the forearm, the elbow joint acts as a fulcrum across which the muscles perform the effort. In order to rotate a lever around its axis, we will have to apply force. At what angle do you think the force will rotate the bar most efficiently? Well, when the lever is free hanging, it is neutral or parallel with gravity, and the bar does not rotate. When the force pulls the bar at a 90-degree angle to the bar, or perpendicular with gravity, the entire force is transferred to rotating the bar. So what would be happening at the angle between these two vectors? Well, the bar does indeed rotate, but not at the same efficiency as at the 90-degree or perpendicular to gravity. That is because at this angle, the force actually splits into two different directions. Here you have the rotary component part of the force, the parallel component part of the force, and then the portion in between. Now, transferring this knowledge into the human body and free weights. In this case, the forearm is actually the bar, and the weight is the force that pulls downwards. The force of the weight will always pull downwards. This is the force of gravity. Therefore, when the forearm is parallel to the ground, the angle between the force and the forearm is 90 degrees, which causes the force to pull and rotate in the forearm in the most efficient manner. In this state, the elbow flexors work relatively strongly, as it is a maximum lever, in order to resist the force that pulls downwards. So, at what angle will the elbow flexors perform almost no work? When the dumbbell moves nearly perpendicular to gravity. In this state, the elbow flexors hardly exert any effort whatsoever until the bicep is pulled from the neutral position. At all other angles, we'll be resisting only a portion of the weight. Now we need to speak on the direction of pull in relation to the levers, as this has a large impact. The effectiveness of the muscle force in producing rotation is greatly influenced by the angle of pull. The angle of pull is the angle of the muscle's attachment in relation to the bone. Not all of the force produced by the muscle is put to use in generating rotation of the bone. Here you can see where the force is actually being distributed. Depending on the angle of insertion of the muscle, some force is directed to stabilizing or destabilizing the bone. At angles less than 90 degrees, only a small part of the muscle effort will produce rotation, while a major part contributes to the joint stability. Here you can see an example of how most of the force is going upwards, while only a small portion is bringing the limb forward. This results in high joint stability. However, when the forearm, in this case, is perpendicular with gravity, 100% of the force contributes to the movement, making this a 100% active lever, or basically where the muscle is loaded the most during the range of movement. When the muscle's angle of pull is greater than 90 degrees, only part of the muscle's effort will produce joint rotation. The majority of the force will be spent pushing the bone directly upwards, stabilizing the joint. The antagonist stabilizer may assist in joint stabilization by countering the rotator force of the agonist, or in this case, the biceps.